Hey, John here. Let's talk about doubly linked lists now, okay? The way these things work is there's two links in each node instead of just one. So they're going to be two pointers. So let's say this is node 1, and then he is followed by node number 2. He's up followed by number 3. This is the last one in the list. So what do we do with these extra pointers? Well, in a singly linked list, we go from front to back, from the head to the tail of the list, right? But you can also have another list that goes the other way at the same time. Okay? Well, I guess I should draw that arrow like that. This one then comes over and points to node 1. And this one here is null. So we can then have tail. Now, as you can see, what we really have here are two singly linked lists at the same time. One that goes from the head to the tail, and the other one that does exactly the opposite order, all right? So one of the benefits of this, well, remember in a singly linked list, if I wanted to delete node number 2, I really had to tell the delete function where node number 1 is, because node number 1 is the thing that points to 2, and I had to redirect the pointer around 2 to 3 in order to get rid of 2. Now, if I simply have the address of node number 2 and no other information, I can delete node number 2, because 2 tells me where the previous one is, and it also tells me where the following one is. And that's true about the head and the tail as well. There is no previous node for the head node, and there's no following node on the tail node. All right, so you'll end up, let's say we wanted to delete node 2 now. I would say go to number 2's next node's previous pointer. And I would replace it with the value from here, right? Which would cause that node's previous pointer to point now over to 1. And I can do the same thing with number 1 here. I need to replace this pointer here. I gotta make it point around a 3, right? So in that case, I can take this guy here and copy it over into node 1, who now would then point over to number 3. Okay, thus this link goes away, and this link would go away. At this point in time, no one's pointing to 2 anymore, and you could just delete it. So what else can we do with this? Well, we can always insert and delete nodes at the head of this list quite easily, because the head node always points right here, just like we did before on a singly linked list. There may be a little extra to deal with if there was only one node in the list, or none, right? Because the tail would also have to point to the same one. Well, we could also do quick and easy adds and deletes from the tail of the list, because remember, these are just two singly linked lists. So operations at the head of the list are fast. Operations at the tail of the list are fast. Operations in the middle of the list are really kind of the same as they were with the singly linked list, except for they are simplified in that I just showed you what happens with a delete, where you get to use a more intuitive method of saying, I want to delete node number 2, rather than I want to delete the node that may have come after the predecessor to node number 2, like we did in singly linked lists. All right, let's look at some code. So in this example, we've got a node, and just like we had with our singly linked lists, we have the notion of a next pointer, and it has a value. We have a constructor that sets the value. I'm going to initialize the next and previous pointers to null pointers during the construction of the object. That's how you do that with curly brace initialization. Okay, so really the only difference between this and a singly linked list is that it has a previous pointer, all right? My print list routine will still traverse the list same as it did before down here, but I'll print the previous pointer as well as the other fields. I'm also decided that I want to make sure that my head and tail pointers make sense to me during the dump of the element values in the list, so I want to print both the head and the tail, but otherwise this traversal is no different, okay? Let's go down here and look at the brute force method of creating and filling in a doubly linked list. We've got a head, and we have a tail. We initialize them both to null, representing the empty state of the list. We're going to print out the empty list. for debugging, make sure that these are null pointers essentially. Then we're going to create a node. We're going to create a new node whose value is 1. And in order to add it to our doubly linked list, we're going to set the head and the tail pointer both to point to our new node, because that is both the head and the tail at that time. And we're going to print out our list to make sure that everything got linked correctly and all the values are right. After that, we're going to create a node number 2. Now we're going to put this one at the head of a non-empty doubly linked list. Well, what do we need to do in that case? We need to set the next pointer of node 2 to point to the old head of the list, just like we did with singly linked lists. But we have to also set the previous pointer of node 1 to point to our new node, because it has to go backwards as well as forwards, right? So p head, we haven't modified it yet, so p head is still pointing at node 1 up here from this assignment right there. Okay, so I set its previous pointer to the new node number 2, and we then set the head pointer to node 2, leaving the tail pointing at node 1. Again, we want to dump this out to make sure we have all the right values. Let's look and see what happens. Now we add a node to the tail of a non-empty list. Well, this is going to be exactly the same as the head, but we're going to reverse the nexts with the previous's, right? Because we're going to insert it to the, in a way, the head of the tail of the list, okay? So we're going to create a new node, set its value to 3. The constructor set all the next and previous fields to null. Then we're going to set the previous pointer in node 3 to point at the current tail. Then the tail's next pointer has to point to my new node in order to add me to the end of the list. And the tail is then updated to reflect the fact that PN3 is the new end of our list. Again, print them out, and we're going to see if all the values got updated correctly. So what does it mean to insert something into the middle of the list, say after node number 1 in this case? All right. Now we've saved the addresses of node 1 and node 3 as we were going along, specifically so we can do this. So what do we got? We're going to create a new node. We're going to set my new node's previous pointer to point to the one that we're going to go after, right? We're after node number 1. So I got to say previous pointer equals node 1. My next pointer is node 3. Now notice that this is also the same thing as doing this, right? Because we're actually between 1 and 3. So we can simplify the code and not have to remember both the previous and the next ones when inserting here. We're going to set the next one, pointer of the previous node now to the new node. So what's PN4 previous is really PN1. So we're setting PN1's next pointer in this piece of code to point to the new node. PN4 next is currently pointing to node 3. And we're going to set node 3's backwards pointer, its previous pointer, to the new node. And now we're in the list. We're going to print them out and make sure that all the links are correct. All right, so let's try running this. Let's see what we get. So the first thing we did is print out the empty list to make sure that it makes sense. So head and tail are both null. That works fine. We then insert one node whose value is 1 and print the list out again. Then what do we get here? We got the head and the tail both point to the same node. That node is CD280, the ending of its address. That node's next and previous pointers are both null, representing it's both the head and the tail of the list. We then insert another node whose value is 2 into the head of the list. All right, so now what happens here? The head of the list changed from 280 to 2A0. And the node at 2A0 is the new node, number 2. The next pointer in the node 2 is 280, so that points back to node number 1. And node number 1's previous node is 2A0, so that all makes sense. So, you know, node 2 points to 1, and node 1 points back to 2. And the head and the tail pointers make sense as well. Perfect. So then what happens? we insert another node onto the tail of the list. All right. So in this case, the head points at 2A0, and the node at the head at 2A0 is value 2. That still makes sense. It's the head of the node, so its previous is null. The next pointer and node number 2 points at 280, which is node number 1. Now, node number 1 has a next pointer that goes to 2C0, and that's the new node number 3. And its backwards pointer goes to 2A0, which is node number 2 up here. So this is both its previous and next pointers filled in now. Node number 3 at 2C0 has a next pointer of null because it's at the end of the list. It's the tail or the back of the list, depending on which terminology you want to use. And the previous pointer from node 3 points back to 280, which is node 1. So this makes perfect sense. Down here, we insert node number 4 into the middle of the list. Okay, so what happens here? The head of the list points to 2A0. The tail is 2C0. 2A0, remember, is node number 2. This previous is still null. That looks good. The next pointer is 280, which is node number 1. Node number 1's next pointer is 2E0, which is node number 4, the one we just created. Its backwards pointer, its previous, is 2A0, which comes back up here to the front of the list. That looks good. And the next node after node 1 is the new one, number 4. Its next node is 2C0, which is down here. Node 3, its previous pointer, makes sense because it points to 280, which is this guy up here. All right, so the next pointer after number 4 goes over to number 3, and number 3 is the last, so his next is null, and his previous is 2E0, which is node 4. So all these links line up, make sense. We've just verified that all of that code works perfectly. All right, now that we know the basics, let's put together a class that can hold a list of these doubly linked nodes. All right, so the node isn't changed since the previous example, but I've created a stubbed in this class that we're going to finish off here. All right, so I want to create a node list class. It's going to hold the head and the tail pointer. I'm also going to keep track of the count, the number of nodes in the list as I go. Now I've stubbed in a bunch of these functions here. We have a constructor, and there's nothing for the constructor really to do because I use curly brace initialization on all 3 of these fields. So this probably will never have anything really to do. The destructor should empty the list, okay, before the list container itself is deleted, right? So I'll put a XXX comment in here to remember to go back and deal with that. So I've documented a couple of these stubbed in functions that I want to be able to provide, right? So given a list, I'd like to be able to insert a new node at the front of the list. I'd like to be able to insert new nodes at the back of the list. I'd like to be able to insert a new node after some existing node, all right? So in these cases, the way this would work is I'm going to say insert front maybe, and I would give it a value. Like I want to put a new node in the list with a value of 3. So this function will create a new node. So it'll say like node star p equals new node value to create the node, right? Then it'll put it into the list, right? So I'm going to put a XXX there to let me know somebody better finish that. When this is done, it's going to return a pointer to a node, right? So it's going to return a pointer to the newly added node. So ultimately this will end like this, and I'll have to put the links in here that we just were looking at in the hard-coded example, okay? Insert a new node on the back of the list. Well, that'll basically be the same thing. So I'm going to just copy these 3 lines here. The same structure, right? But it'll hook it at the end instead of the beginning. This one here, insert after. It will do an insertion after this node that is referenced there. But it'll still create a new node with the given value and ultimately return it, okay? We need to be able to delete the front node of the list, delete the back node of the list, delete a specific node from the list. All right. It'd be nice to have a way to get access to the nodes in the list, like front. Give me the front node. Give me a pointer to the front node in the list. Turns out that's trivial, right? Because all I need to do is return this. P head always points rather to the front node in the list. So all I really need to do is this. If I spell it right. that function is done. And what do we do to return a pointer to the back of the list? Well, we just say, what is it, p tail or something? I probably should have called those front and back, but these are head and tail, front and back, all the same, right? P tail. And they're like mixing my terminology in the same class. I'll leave it as a task to the student to straighten all that out. So anyway, yeah, that'll give us access to the end of the list, the back of it, the tail of it. What do we do if we want the next node given a node? Well, that's easy enough. P node, P next. See, I don't know if it's P next or next. It's just given a node. I want the next one. No, that would be that field right there. Okay. So these ones are the easy ones. What is the given a node? What is the previous one? Well, that's just prev. Okay. I mean, given a node, you can just reach in the node yourself if you really want to and grab these pointers if you want. Okay, so, oops, yeah, here we are. Where were we? Next, previous. All right, my print routine that you saw earlier, I just moved it into the class. I call it dump instead, but it does the same thing. It'll just print out the head and the tail and all of the nodes that are in the list in order from the head to the tail. And how would I want to use this object? Well, I want to be able to create one. And here's me dumping the empty nodes, all right, the empty list rather. I'm going to insert and dump, insert and dump, and so on. I'm going to create the same list with the nodes in the same order that you saw in the all hard-coded version, right? So how am I going to insert number 4 after node number 1 here, okay? I could have saved a pointer rather up here to node 1 if I really wanted to, and then used it down here in the insert after and give it, a pointer to node 1 down here. But let's test out some of these other functions while we're at it, right? So I'm going to build a list that looks like this with the nodes in this order. If I call n.back, we already wrote that function, it'll give us a pointer to node 3. And I can go ahead and print out that address, make sure I have it right. I can compare it to what I get from the dumps over here. And then I can say, give me a pointer to the previous node, the node in front of the given one right here in P, right? So it'll say, I got a pointer to 3. What's the one before that? Well, the one before that at this time will be node number 1. And I'll go ahead and say back -1's node address is whatever P is right now. I can then say insert after P, because it's pointing to node 1, a new node whose value is 4, and it should give me a list that looks like this. Then I can dump that out. All right, so this doesn't look too bad. I just have to finish these functions, right? Okay, given all the where we're going here, the delete front makes a certain amount of sense for the destructor, right? What are we going to do to get rid of these when we're all done? We're going to say delete front, and we're going to do that until we don't have any nodes. Well, count is greater than 0. Delete the front node out of the list. And, when the list becomes empty, then it's okay to proceed. So that's all you need to do for the destructor. What does it mean to insert a new node in the front of the list, right? Okay, here we go. We have a new node, and we've got all the front and head and tail pointers and all that stuff up here. So what are we going to do? Among other things, we're going to add 1 to the count, okay? And we are going to do what? We've created a new node. New nodes are initialized, okay? So we don't have to worry about setting all the pointers to null or anything like that. What are we going to do here? We know we're going to be the new front of the list. So I can say P next equals head. Okay, so my new node is going to be in the front of the list. Therefore, the next node will be the old head of the list, right? This is just like the singly links list examples. There will be no previous pointer because I know I'm in the front of the list. I need to make sure that if this new node is not the only node in the list, that the second node points back to this new node, right? So I'm going to have to say if pNext is not null, then pNext previous equals p. Link node number 2 back to this new node, right? And then when I'm done with all of this, I need to say I'm the new head node, right? So does that cover all the cases, right? I'm the head node. Anything that exists in the list will point back to this new head node. This head node points to what was the head of the list. And I am, as the new node, the new head of the list, and we count it. That looks pretty good. Who knows how many mistakes I'll make in here. Let's go ahead and run this and see what happens, all right? Now, what's going to happen in our code, let's think about this for a minute. We don't have any of these other functions done yet, so let's just say if 0. And we also know, oops, that if we construct this and we put stuff in the list, when it's destructed over here, because we haven't written all the code yet, we got to think about this. This routine here is going to call delete front until count becomes 0. So the destructor is going to call this to delete things, and they're not going to go away. So this is going to cause us to have our program will go into an endless loop. So what I'm going to do is comment this out for now. Okay. Make sure that at least we can test what we have so far. So what we can do here is we should be able to dump out an empty list. We should be able to insert a bunch of front nodes and see the list being constructed if it compiles. Okay, it did compile. That's good news. What are the odds? You write code, it compiles the first try. It probably won't work correctly. Let's have a look-see. Here's my empty list. That worked. Here is a list after one insertion. Oh, I made a mistake. Look what happened here. The head node pointer was updated to point to the new node at 0280. Does point this. The next and previous pointers in the new node makes sense. The new node value makes sense, but it is also the tail. I screwed up because I forgot the special case when I'm inserting into an empty list, the new node that I'm putting in the front of the list is going to have to become the tail as well. But we'll go back and fix that in a minute. What happens if I then insert another new node at the head of the list? The head points to the new node number 2. That previous is null. That makes sense because he's the new head. His next points to 280, which was the old head of the list, and that 280 looks good. The next pointer of node 1 here is null because he's at the end of the list. The previous node pointer in node 1 now points to the new node at 2A0. So that looks good. So far, the only mistake I can see is this thing up here. The tail was never set. What happens when I insert node 3 and then dump? So node 3 did not get inserted, so there's something wrong there. Let's have a look-see. First of all, let's look at the main. Oh, that's because they said insert back, and I didn't write insert back yet. So there's only one bug in this code so far. Let's look and see what we got going on in here. So when we're in the front node, along with phead, we have to say if tail equals null pointer. You could also ask like if count is 0 in here, right? Because if the count is currently 0 before we do this, then we know that there's no nodes in there. Okay. Oops, let's put a comment over here. Special case, inserting into empty list. All right, compile it, run that one, and we're already looking a little bit better. Empty list looks good. Put one node into an empty list. It's the head node, it's the tail node. Its next and previous are both null, and it has the correct value. Everything's fine. We put a node number 2 into the head of the list. The head now points at 2A0, and that is the address of this new node number 2. The tail points at 280, which is the last one on the list. That's good. The first one does not have a previous. That makes sense. First one does have a next that does point to the next node. The next one is node 1, and its previous goes back to the first one, and the last one's next is null. That makes sense as well. And this is the other dump because we added a node using the push back, or the insert back that we did not yet write. Now, we did this before in the hard-coded logic, and we know that when we insert in the front and the back, it's a symmetric operation, right? So I should be able to just copy these lines. 8 lines right here. And paste them right there. Now we have to reverse it. Now, here's the problem when you're copying and pasting code. You could easily screw this up. Right? Because by forgetting to change one of these many items in here. So let's think about this really for sure as we're going on. When we create a new node that's going to be at the end of the list, this is the previous pointer, will point to the current end of the list. If said previous pointer is not null, then the previous node's next value points to the new node. So, oops. I'll say the old tail node. That should be more clear to this new tail node is what this might be say. All right. Now I am the tail. Right. So let's think about this. Make sure we got it just right. Create a new node. My new node's backwards pointer, the previous guy, is the current end of the list. And if the list is empty, that would be null, and that makes sense. If there is something there, reach back into the previous node, which is the current tail of the list, and set that node's forward pointer, the next pointer, to the new tail node. The new node becomes the tail. Okay, so now we can say, what happens if we go into an empty list? Again, the symmetric thing of what I screwed up last time, right? So this one has to say, what if the head is null? Then it turns out I'm the only one on the list, and make sure that that case is taken care of. All right, so hopefully I got this right. And if we run it, this third one down here, insert back, should work. So after the third in the third list dump, we should see node 3 added. And thank the stars that it did work. Okay, so let's look closely here. We didn't change anything up here, so the first couple of cases are fine. We added node 3 by calling insert back. So the head node points to A0. That's this one here. And this head node is number 2. It's the head node, so that should be null. It points to a next node at 280, which is the node number 1, and that makes sense. Node number 1's previous node comes back up here to the first node. That makes sense. Node number 1's next node pointer comes down here and points to number 3. Number 3's previous should point back to number 1. It does. Number 3 has no next node because it is the tail. And the value is 3, so that works. Yeah, that all looks pretty good. So what if I want to insert a new node after some given node? All right, what do I got to do in that case? Well, I, by definition, have to be inserting into a non-empty list. It could go into the middle of the list, or it could go onto the end of the list. But because I said insert after, it's not possible for this to ever be called to insert a new node into the head of the list, or the front, okay? So let's figure out how that's going to work. All right, so I got the new node. I'm given a node. Well, I know I'm after that node. Therefore, what? The P node next will have to equal my new node. My new node's previous pointer must equal, when we're done, the P node. All right. Now we can't really do this one first. Okay, we're going to see why in a minute. We'll destroy that before we use it. My next pointer is what has to equal the previous one's next pointer before I destroy it. So I'm going to reverse this order. I can update the fields in the new node first because no one's using them yet, right? So let's not destroy anything anywhere else until this new node is set up. I'm guaranteed that my backward pointer will point to the guy I need to be after. I need to make sure the guy that I'm supposed to be after points back to my new node. And I need to make sure this will compile. So my next pointer goes back to the next node after the previous one. Okay, that all makes sense, right? Because I'm after P node, so P node's current next node is going to become my next node. That's what this does. All right, and then when I'm done with all that, the P node that I come after has to be pointing back to me. Now, what about the guy that comes after me, right? So if I say if, I have to ask, right? Because what if this is null, right? It turns out that if this is currently the end of the list, and I'm going to be inserted after that end of the list, then I'm going to become the new end of the list here, right? And my next pointer will be null. So I need to make really sure I don't do something like P next previous equals P, right? I could end up with a seg fault here, right? So what is this doing? It says if there's a node that follows the thing that I'm creating, or that will be following the thing that I create, go down into that one that is following the new node and make sure its backwards pointer points back to this new node. So that should look good. That looks right to me. Count it. Now we have to ask one last thing, right? If the new node becomes the new tail node, I have to update the tail pointer. So I can say if what? If p tail, is that what I called it? P tail? Yes, right here. That's the end of the list. If the tail is currently pointing at P node, it makes sense that it should now point to the new node, right? So this is true if I'm being inserted after the current tail node, in which case this new node needs to become the tail node. So that all makes sense, in my opinion. It probably will work. Let's try it out. Alrighty. What did I do? I don't even remember what I did. Oh, insert after. Okay, so that's down here. We didn't even test it yet. We can go ahead and test it up here. Let's go ahead and do an n.insert after 999. What do we want to do? I want to insert after like pn3. We're going to hang on to pn3, right? So that way we can use it down here. So this is going to test after node number 3, which is currently the tail of the list. And it did not work because we dumped out. Oh, wait a minute. Always debug your debugging code. I inserted, but I did not dump out anything. That might help if we printed something. Okay. So what do we got going on here? It's empty. We add node number 1. We've already checked these routines. 2 points to 1. 2 points to 1 points to 3. Now here is the dump after I called insert after 3 here. So what do we got going on? We need to check to make sure that the list is not damaged. So before I called insert after, the list started with A0. The tail node was at C0, which was node number 3. When we're done, the list still starts at A0, which is a good sign, and it ends at something else, which is also a good sign, because we know that this particular test added something to the end, and you can see it down here at the end of the list. So let's make sure everything got linked in here right. So A0 is the head node. That's number 2. It makes sense. The previous pointer looks good. It then goes to 80. 80 links to C0, and it links back to A0. That works good. So I got 2, 1, and 3 now down here at C0, which is the one that comes after node 1. Its next pointer goes to E0, which is good because that's the new node. It should. Its previous pointer points back up to 80, which is right for going back to node number 1. Now, node at 32E0 is the new tail, so the new tail got updated correctly. Its next pointer is 0, which makes sense because it's the tail. And the previous pointer here is at 32C0, which points back to node number 3, and the value is 999. Everything is perfect. That's great. So I think we got these right. Okay, so we got the ability to insert after an existing node. Let's make sure it still works, even if we don't insert it at the end of the list. Let's remember where node 2 is and insert after that and rerun our test, right? Because that's a different case. Uh-oh. Well, now PN3 is not used. Okay, too many. Compiler warnings are set too high. But that's fine. We can just go ahead and delete this. Run it again. So now what happens? You can see that we are up here in the middle of the list this time. So we inserted it after node 2 that we kept track of after node 2 was created, right? Let's take another look at that to make sure we got it. So I inserted node 1 in the front, then I inserted node 2 in front of node 1, and I remember where node 2 is, so that's good. This all makes sense, right? So we create 2, 1, 3 in the usual order. Nothing changes there. Now let's see what happens here. We got 2A0 is node 2. Its previous pointer looks good. Its next pointer is 2E0, which is the one that was supposed to follow it. That looks good. The previous pointer in the new node here goes back to A0, which comes back to the beginning of the list, which is nice. The next pointer, 280, goes to node 1, and that makes perfect sense. Node 1's previous pointer at 2E0 points back up to our new node. So this node did get correctly linked into between 2 and 1. 1 then continues on its next pointer at C0 down here, which is node 3, whose next pointer is 0. And previous pointer at 280 goes back to node number 1. That all looks good. The tail node address is at 02C0, which points down here to node 3. So that means that we did not accidentally store our new node address in here into the tail by accident as a result of perhaps incorrectly implementing the check to make sure that I need to be linked in at the tail node that we discussed a few minutes ago. Okay, so those are your insert routines. Those all look good. What does it mean to delete the front node, the back node, and the node in the list? Well, to delete the front node, first of all, we need to ask if there is a node. You don't want to delete a non-existent node. In fact, we can collapse these. If we wanted to, we could just write one delete node function. And then we can just call it from delete front. So we can say, if we want to, delete node, p-head. Done. What's the back? Delete node, p-tail. All right. Now we got to deal with this one. Why? Because somebody might try to delete the head or the tail node anyway by just passing its address to the delete node routine. So why bother writing all these other variations? Just write one universal one. Okay. So what if, what are we going to do? We're going to say if p node next, if it has a next pointer, we need to reach over into the node following the one we want to get rid of. And change its backwards pointer. So if I'm not the tail of the list, go to the node that follows the one that's being deleted, right? And take its previous pointer that currently points to this guy here, to myself, and set it equal to my previous pointer. To take to take p node here out of the chain of links pointing backwards, all right? If p node has a previous pointer, it says if this node is not at the head of the list, then go back into the previous node and set its next pointer that currently points to the p node, to the one I'm deleting, and set it to the p node's next pointer. Right? So that just disconnects p node from the backwards chain of links and from the forward chain of links. Then we can simply ask if the head of the list is pointing to p node, then set p head equal to p node next. All right, if the head is pointing to the one I'm going to delete, then the head needs to point to whatever came after the one that's being deleted. And if it turns out that this node is at the tail, that next pointer will be null. And that's exactly what you want to put in p head if you're deleting the only node from the list. And we got to ask if it was the tail and do the same thing. If this is the tail of the list right now, then p tail equals p node previous, right? So point to the node that comes before p node if p node is currently the tail. And if p node is the only item in the list, just like with the head, the previous node pointer in p node would be null, and that would leave both p head and p tail set to null at the same time, which is perfect. What you want to do if the list becomes empty, you of course have removed something, so you want to get it out of the count, right? And that will be the same thing you want to do in all these cases up here anyway. So I think I just implemented all three of those. We have all three inserts. We have all three deletes. We can come back up here now and let the destructor run. Okay. Because now this function does something. Ultimately, it will reduce the count, even if it doesn't work. And I made a mistake. At least we know that delete front will come down here and call delete node, and whatever delete node does in here, whether it's correct or not, it will decrement the count, and that loop will eventually end, even if I wreck the list. Okay? So what else is left? We get the front, the back, the next, the previous, the dump. I think we just finished the entire class. Well, what are the odds of that, right? Let's make this. What are the odds that it actually compiles? There's no way it's going to run. You can't write code that works on the first try. It's just crazy. Of course, we didn't write any test code. That's why it worked perfectly, right? let's just go for broke here. All right, so we got this one here. We inserted the 999 after the 2. So what's the state of the list after this? Let's make sure that we get it nicely documented, because what's going to happen is, all right, let's just remove the, let's just remove this code here from our test case, right? And it'll gripe because we're not using this anymore. Okay, so the reason I did that is because I already documented down here what the condition of the list will be in. Let's just delete all this, given the scenario that we started with up here, okay? So what are we going to do here? We're going to go to the back of the list and say, here's the back node I got when I called n back. Then I'm going to say, give me the node before that. So this will leave P pointing to node 1, this guy right here. And I'll print that address out to make sure I got it right. Then I will say insert after the given node, which is going to be number 1 at this time. And it'll put a new node 4 between 1 and 3 and link it in like this. And we just tested our insert after function, so it should work fine. Let's see what happens. Well, we can see the 4 sitting right there. So let's make sure. I'll get a bird's eye view here. Here's the empty list. We insert 1 and print. We insert the 2 at the front of the list and print again. We didn't change any of this code, so I'm sure this is all fine. So we've got the list where we got 2, 1, 3 up here. Then we said, give me the back of the list. And it returned this number here, which ends in 362C0, and we can clearly see that it did return a pointer to the last node in the list, which is number 3, node 3. Then I called, get the previous node, and it gave me 36280, which is the value of this pointer here, which does point to node number 1. That makes sense. And then it says insert after node 1, put a 4 in there. So we can see we got node 2, we got node 1, we got the 4 node here, and then we've got the 3 node. Well, let's make sure 4 is linked in correctly in both forward and backwards lists. So node 1 here has a next pointer that goes to 362E0, which is node 4. Its next pointer goes to 362C0, which is node 3, and his next pointer is 0. So going in the other way, node 3 being at the end of the list at 326C0 is the tail. So we didn't break the tail somehow, which is nice. And the last node's previous pointer points to 326E0, which is our new node. And its previous node goes to 36280, which is also the correct previous node in this order. And of course, we didn't touch this, which goes to 362A0, which goes back up here to node 2, and his previous pointer is 0. So there you have it. There is a class that implements a doubly linked list and provides various accessors and things. Now, I did this a little bit different than the way you would normally see a doubly linked list class designed. It doesn't really match the C++ standard. It provides all of the functions in the correct way, but usually there's not an insert after function, okay? And usually there's not a delete node function either. This works a little bit differently, and I did this on purpose so that I can leave it as a task to the student to implement another kind of linked list or a templated class, right? This thing is not even templated. This is hard-coded. This is a node that only holds integers, and here's a class that holds a doubly linked list of node structures here that hold integers. Okay, so again, this is not normally how you would do this, but this should be a very good illustration on how doubly linked lists work and how all the operations are implemented. You can now take this and make anything you want out of it using these general constructs to build your own doubly linked list classes that have whatever API you want. Thanks for watching. We'll see you next time.